Hello everyone, this is 8.2, which will be discussing the union, intersection, and complement of events, as well as odds. And let's just first recall what intersection and union are. So for events A and B that are contained in some sample space S, A union B is the set of all elements such that, well, the element is either in A or in B, so the keyword for union is or. Similarly, the keyword for intersection is and. So union is any element that is either in A or B, whereas intersection is just, well, the elements that A and B share in common, basically. And by the way, if A and B do not share anything in common, they're called disjoint or mutually exclusive events. All right, and now we'll get on to probability of the union of two events. And this is pretty important, actually. So here, this is kind of what we need to know. This is like the big equation here. And it says probability of A union B is the probability of A plus the probability of B minus the probability of A intersect B. And this shouldn't make a lot of sense if you recall how we calculate the number of things in the union. It's just the number of things in each one added together minus the amount of things in the intersection because of over counting or double counting. So when you count things in A and things in B, you may be counting things that are contained in both if you kind of count each one at a time, so there's double counting basically. So this will account for the double counting. We discussed this, by the way, in chapter 7. I forget what section it was. I think it was 7.3 if I'm not mistaken. Oh, by the way, if the intersection of A and B is empty, then the probability of A union B is just their sum because, of course, probability of an empty set is just 0. So that's a little easier. We'll see an example of that actually, but first let's take a look at this example. So for this example, we're asked what is the probability of drawing either a 2 or a diamond card in one draw from a standard 52 card deck. So really what it's asking is, let me label it like this, probability of drawing 2 or drawing a diamond. Now, drawing a 2, let's say, is the set A, and drawing a diamond is the set B. I could write 2 and diamond itself, but then I don't want us to get confused. We're not finding the probability of the number 2, we're finding the probability of the set drawing 2. So we'll kind of hopefully make the distinction here. So this, of course, according to this formula here, is the probability of A plus the probability of B minus the probability of the intersection A and B. Now, the probability of drawing a 2, well, let's see if I think I have some space here. So what's the probability of drawing a 2 from one card, from one draw? Well, how many 2s are there in the set of a 52 card deck? And then at the same time, how many number of cards are there total? So again, if it's one draw, then that means we're drawing from a total of 52 cards. So the number of things in the sample space is 52. The number of 2s, so the number of things in the set of possible 2s that you can draw from, well, remember that there's a 2 for each suit. There are 4 suits. So there's the 2 of diamonds, the 2 of spades, the 2 of hearts, and the 2 of clubs. So there are 4 actual 2s you can draw from. So in total, our probability after reducing is 1 over 13. Okay. Similarly, what's the probability of drawing a diamond? So the probability that we draw a diamond, this is a little different because how many diamonds are there? There's actually 1 for each rank. So there's 1 for each number, basically, as well as for K, Q, and J. So there's the ace of diamonds, the 2 of diamonds, 3 of diamonds, all the way to 10 of diamonds, and then there's the jack of diamonds, the queen of diamonds, and the king of diamonds. So that's a total of 13, which makes sense because 4 times 13 is 52. So this is going to be 13 over 52, which reduces to 1 over 4. So we have to add these numbers, 1 over 13 and 1 over 4, and we have to subtract by the probability of the intersection. Now, this is where things get a little interesting. Is there an intersection between cards that have 2 as their rank and cards that have a suit of diamond? And yes, there is. So what I'm asking is there a card that is a 2 and also a diamond? Yes, it's the 2 of diamonds. So the probability of the intersection is really the probability of drawing a 2 of diamonds. So the 2 diamond means 2 of diamonds. And of course, there's only one 2 of diamonds in the standard 52 card deck. So its probability is 1 over 52. So now all we have to do is add these two numbers and then finally subtract this one. All right, so that shouldn't be too bad. We'll just find a common denominator. So now we have that our probability is, so I don't want this to get in the way too much. Let me just say this. So the probability of A union B is 1 over 13 plus 1 over 4 minus 1 over 52. What's kind of funny about this is that we actually shouldn't have reduced these because we have a denominator of 52. So really I'm going to write, instead of 1 over 13, allow me to rewrite this as 4 over 52. So really I want to use this version of it. Similarly, I want to use this version for the drawing the diamonds. So that's 13 over 52. And in total, what do we get? We get 4 plus 13, which is 17. And then 17 minus 1 is 16, so it's going to be 16 over 52. And now since this is our final answer, we can reduce this. And this, by the way, reduces to, if you divide by 4, that's 4 over 13. And if you want to write that in decimal and then convert to percent if you like, you can do that as well. But I'm going to leave it like that, 4 over 13. And now we're going to take a look at a few more examples where the situation's a little different. But we can still see that we'll be applying this when we want to find the probability of doing something or something else. I said we were going to do a few more examples, but we'll really just do this one example before moving on to the next topic. But it's going to be 2 parts, so it's kind of more than one example. So let's say we roll 2 dice. So suppose 2 dice are being rolled. And these are 2 separate questions. So the first one says, what is the probability that the sum is 7 or 11? And in order to find out, well, just so I don't have to write too many words here, we want to find the probability that we roll a 7 or we roll an 11. So again, when I'm writing these numbers, they represent the set of that possible roll. So probability of 7 doesn't mean the probability that doesn't mean the probability of the number 7, but it means the probability of rolling a 7, which I know sounds kind of weird. But just know that I'm not talking about the number, I'm talking about the number as a set. So I know the notation gets a little funny. But again, we know this is the probability of rolling a 7 plus the probability of rolling an 11 minus the probability of rolling a 7 and 11. Okay, so first let's talk about these two. Rolling a 7 and rolling an 11 individually. So what is the probability of rolling a 7? Well, how many ways can you roll a 7 divided by how many total possible rolls are there? So remember, we actually discussed this in chapter 7. You'll have a total of 6 choices for each die because it's 6-sided dice. Now, since you have a total of 6 possibilities for each one, you're rolling 2 dice, there's a total of 6 times 6, which is 36 total possibilities. And I'll discuss a little bit of the calculation of what the ones for 7, but we wrote them as ordered pairs. So we said that you can roll a 1, then a 6, a 2, then a 5, a 3, then a 4, a 4, then a 3, and then, well, just these reversed. So then a 5, then a 2, then a 6, then a 1. So these are the only possibilities of rolling with 2 dice a total of 7. The first one's either a 1, then the second one would be a 6. The first dice would be a 2, then the second a 5, and so on. So there's a total of 6 possible outcomes here. So we have 6 possible outcomes of rolling a 7 divided by 6, well, 36 total rolls. And if you reduce this, it reduces to 1 over 6. Perfect. Now, similarly, what's the probability of rolling an 11? So the probability of rolling an 11, we have to do a similar calculation, but now for 11. And there's not that many, actually. I think it's really just, well, let's see. So remember that our calculation for rolling a 7 started with 1, then whatever number you needed to complete that. But if we create an ordered pair starting with 1, you'd have to roll a 10 to make it 11, and the die only has numbers 1 through 6. So it can't be 1. In fact, it can't be 2, because then you would need, well, you need a 9. So you kind of see where it's going. In fact, really the largest number, or I guess the smallest number where we can actually start this is 5. Because if you roll a 4, you would need to roll a 7, and there are no 7s. But if you roll a 5, you can roll a 6 then, and then similarly, if you roll a 6 first, then you can roll a 5 in your next one. So these are the only two, so this is going to be 2 over 36. So the sample space is still 36 for each of these because you have 36 total possibilities of rolling 2 dice. And that reduces to 1 over 18. Good. Now, the fun one. What the heck does this mean? Well, just kind of think for a little bit. The previous problem I wanted to do first before I did one like this, because that I think opens your eyes a little more. It's possible to draw 2 and a diamond at the same time, and it's the 2 of diamonds. Is it possible to roll 2 dice and that the result is 7 and 11 at the same time? The answer is no. It is impossible, actually. So for that reason, the probability here is 0. And the reason there is because, well, rolling a 7 and rolling an 11 are disjoint. They're mutually exclusive events. Unlike drawing a 2 or drawing a diamond, because those actually intersect, so those are not mutually exclusive events. Meaning, all we need to do now is just, well, add these two. So these two combined tell us that the probability of rolling a 7 or 11 is 1 over 6 plus 1 over 18. And really here all we have to do is multiply top and bottom by 3. And we get 3 plus 1 over 18, which is 4 over 18, which reduces to 2 over 9 actually. Awesome. So that actually wasn't too bad. Now let's take a look at the second part here. Now here I ask you, what is the probability that both die turn up the same number, or, so this is a different scenario, the sum is less than 5? Well, yeah, we need to find out what the probability of each one is, and then we need to find the probability of the intersection if there is any. In this example, there was no intersection, but here there might be. So let's see, we want to find the probability that, let's see if I can write this, let's just say same, probability that both dice are the same, so we know what that means. And we want to find the probability that, so let me write it like this, same or less than 5. So these names, same or less than 5, mean those events. So that both dice turn up the same, or that both dice turn up a sum that's less than 5. So we know this is going to be the probability that they're both the same, plus the probability that the sum is less than 5, minus the probability that it's the same, they're the same number, and the sum is less than 5. So you can probably think about some scenarios for this last one. This one actually isn't empty as it turns out. Well, anyways, let's see if we can do this. So this requires some calculation, but it's not too bad. So if you can count the ordered pairs where you roll 2 dice and they're the same, there's only 6 choices. Either you can roll a 1 then a 1, a 2 then a 2, a 3 then a 3, a 4 then a 4, a 5 then a 5, or a 6 then a 6. So I'll just write them all out for good measure, but you can kind of see that it's not too hard to get this result here. So as it turns out, there's only 6 different ways you can roll 2 dice and they turn out to be the same number. So as it turns out here, for the probability of them being the same, it's 6 over 36. So let me erase this calculation. So this is 6 over 36. What about less than 5? We also saw something like this similar to this one in chapter 7. But let's see. So if we roll a 1, then the next number has to be something that will make the total less than 5. It can't even be equal to 5. So can you roll a 1 and a 4? No, because that would be 5, not less than 5. If it said less than or equal to 5, or at most 5, which means less than or equal to, by the way, then yeah, you could roll a 1 and a 4. But in this case, the highest the second number could be, if the first one is 1, would be a 3, because that would be 4, which is less than 5. So we can roll a 1 and a 1, we can roll a 1 and a 2, we can roll a 1 and a 3, and that's it for rolling a 1 first. If we roll a 2 first, the second number could be a 2, well, it could be a 1, a 2, and that's it. Because this sum is 3, this sum is 4, and then if you roll a 2 and a 3, the sum is 5, and it's not less than 5. What if you roll a 3 first? If you roll a 3 first, you can roll a 3, then a 1, that's 4. And that's it, because if you roll a 3 and a 2, you'd be equal to 5. So these, as it turns out, are the only 6, there's 6 of them, that actually add up to being less than 5. So this is plus 6 over 36. And now we need to do minus this guy. So, well, here we have the total possibilities of being less than 5. The sum is less than 5. Can we see if there's any intersection between the two numbers in the ordered pairs being the same? And yeah, you can see that right here. And that makes sense, because if you take a look at the pairs where they're the same, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, the only ones that sum to less than 5 are 1, 1, and 2, 2. 3, 3 sum to 6, and that's less than 5. That's not less than 5. So there's only 2 here. So being the same number once you roll them, the 2 dice turning up the same, and there's some being less than 5, there's only 2 possibilities out of 36 total rolls. And there we are. We could reduce this if we wanted, but I'm going to reduce after the fact. They already have the same denominator, so let's just add the numerators. So 6 plus 6 is 12, minus 2 is 10. So we get 10 over 36, which you can divide by 2, top and bottom, and you get 5 over 18. And there we go. So nice. So that was it for this and talking about unions and intersections when it comes to being events and finding those probabilities. And now we're going to take a look at what happens when we want to find the probability of the complement of a set, as well as talk about odds. Right, so first let us recall what the complement of an event is. So the complement of the event A is denoted A prime. Sometimes we use AC, but for this book we use A prime. And these are two pretty well-known facts about A and A prime. They have nothing in common because, well, the complement of A just means everything except A. So of course it won't share anything in common with A itself. Similarly, if you take the union of A and its complement, you get the entire universal set, or in the context of probability, the sample space. So here I've written a Venn diagram just to show the relationship here. And in retrospect, I probably should have shown a Venn diagram for what we saw previously for intersection and union, but that's fine. Here, let's shade A in red. So like for a legend over here, I have this. So A is the red shading, and then A prime will be the blue shading, which is everything that's in the sample space S that is outside of the set A. So you can indeed see that, well, the blue and the red do not overlap, or at least they shouldn't, so that means the intersection is the empty set. Also, if you consider everything is shaded red or blue, which would be the union, is just shading the whole set S. All right, so that justifies these two just by Venn diagram. Now, the probability of the complement of an event is this following equation here. And this is basically due to how you count the amount of things in the complement of a set. Since the union of the set and its complement is just the whole universal set, or again in this case, the sample space, well, the number of things in the complement is just the number of things in the sample space minus the number of things that are in the set itself. So with that being said, if you divide through by the number of things in the sample space, you'll get the probability. So this is, the reasoning of this is basically because the way you count things in the sample space is just subtracting the things in the entire sample space by the things in the original set that we're taking the complement of. Now that's kind of a mouthful, but you can kind of reason that out. So here we say the probability of a complement of a set A is just 1 minus the probability of A itself. Okay. And you know what? Just because I still want to prove this for some reason. I just like proving things. So let me just, to convince you more, let me kind of write here PF for proof. It's going to be a short proof. So the probability of A prime is the number of things in A prime divided by the number of things in the sample space. But since the number of things in the complement of a set is just the number of things in the sample space minus the number of things, so like number of things in S minus the number of things in A, well, then we can split this up as number of things in the sample space over the denominator, number of things in the sample space, minus the number of elements in A divided by the number of elements in the sample space S. So what you notice is that this here is just a number over itself, and that's 1, and this here is just probability of A by definition of probability. So that proves this. So that was what I was trying to say. I know I'm kind of rambling here, but in any event, let's just move on, going on a huge tangent. So let's move on to this example. So here we say that a shipment contains 45 bolts, 9 of which are defective, and quality control for this particular company will select 10 of the 45 bolts at random and will reject the entire shipment if one or more of the 10 that they selected is defective. And this is just so the job isn't too tedious. I don't know if companies actually do this, but I can imagine that it is a technique that's probably used. Anyways, let's see. What is the probability that the shipment will be rejected? Well, first off, here's what we're going to do. We're going to imagine the shipment is not rejected. So let's let E be the set that that is not rejected. So let me just write set of not rejected, or I guess accepted. Now really what that means is that we selected all of the non-9 that were defective in the 45 bolts, because we know in this particular shipment 9 of these 45 are for sure defective. But if we didn't reject, then that means we didn't select these 9. So what this implies then is that the number of things in E is just the amount of ways you can choose, well, 45 minus 9, which by the way, let me write it in blue here. 45 minus 9 is 36. So just to highlight what I'm trying to say here, 45 is the total number of bolts, 9 is the number of defective bolts or bad bolts, and then 36 would be the number of non-defective or good bolts. Okay, so if we didn't reject, then that means all the bolts we selected were non-defective, meaning we selected 36, well, one of these 36. In fact, we selected 10 of these 36. So how many ways can you choose 10 of 36 things? Of course, it's 36, choose 10. And then we can use our calculator to approximate this, but I'm just going to leave it like that for right now. And what now? Oh, so the probability that we do not reject the shipment is just the number of things in E, the number of elements in E. In other words, the amount of ways you can not reject, so the number of ways you can select 10 of the 36 that are good, divided by the number of things in the sample space. Now the sample space is the amount of ways you can select 10 of 45, because that would be all possibilities. But again, E specifically is not rejecting, so that's selecting only non-defective bolts. I know it sounds complicated, but the more you think of it, this is kind of the only way of arriving at the solution here. So we have 36, choose 10 for the numerator, and this has to be 45, choose 10 for the denominator, because again, the sample space is the total amount of ways you can select your random 10 out of the total 45 bolts in the shipment. So this right here is the probability that you actually do not reject the shipment. So that means the probability that the shipment is rejected so the probability that you do reject is just equal to the probability of the complement of E, because not rejecting is, well, the complement of rejecting, and vice versa. So here we want to find the probability of E prime, which from the above equation here is just 1 minus the probability of E. And we know what that is. In fact, we can use our calculator. Let me do that right now real quick. All right, so using my calculator, 36 choose 10 divided by 45 choose 10 is approximately 0.08 if you round. So this here is going to be 1 minus, so let me just write approximately 1 minus 0.08, which is approximately 0.92. That's kind of high. So there's a 92% chance that we'll actually reject the shipment with this method, which I guess is a good thing if you think about it, because that means our quality control is actually pretty efficient, 92% efficient, provided this scenario actually happens. But that goes a little beyond the question, but it just kind of goes to show the practicality of probability and why these methods are kind of chosen, basically because probability. All right, so now we're going to take a look at odds, which, believe it or not, actually has very much to do with complements and probabilities of complements. So let's take a look at that right now. Right, so now for odds, if the probability P of E is the probability of the event E occurring, then we have these two explanations here, these two definitions really. So there is odds in favor of the event E and odds against the event E. So in favor of E is just the probability that E occurs divided by, well, E not occurring. So it's probability of the complement of E. Similarly, odds against E are just the reciprocal basically. So it's probability that E doesn't occur divided by the probability that E does occur. So if you think of, I guess, casino lingo or just betting in general, you'll always see, the word odds being tossed around. So if you roll a 2, let's say out of 1 dice, if you roll a 2, you have 1 in 5 odds of rolling a 2. What that basically means is that there's one way to roll a 2 of the 6 possibilities of rolling 1 dice against the 5 ways to not roll a 2. So that's kind of what this really means. Because remember, probability of E means the probability that E happens. Probability of E prime means the probability that its complement, in other words, E does not happen. All right. Here I just kind of say specifically that the probability of E can't be 1 for odds in favor of E, and the probability of E cannot be 0 in odds against E. And this just ensures that we have a 0 denominator. Remember that P of E prime is just 1 minus P of E. So if P of E is 1, then you have 1 minus 1, which is 0 in the denominator. And here you just get straight up 0 in the denominator. So you don't really need to worry about these too much, but if you kind of think about them, it makes sense that the odds wouldn't exist if you have a guaranteed or impossible event, basically. All right. So now in this example, this has to do again with rolling dice, but here we're rolling 2 dice. So in rolling 2 6-sided dice, there's 2 questions that are being asked here. First, what are the odds for rolling a sum of 7? So basically what we want to know is how many ways can you roll a 7? What's the probability of rolling a 7, and vice versa, what's the probability that we don't roll a 7? And then we're just going to take the fraction of those to actually find the odds. By the way you can write odds, normally we write it as a ratio. Instead of writing it in fraction form, we write it in ratio form, which is like, I guess, colon notation, but I'll get to that shortly. So notice that the odds for rolling a 7, odds in favor of rolling a 7, let me write it. Odds in favor of rolling 7 is just the probability that you roll a 7 over the probability that you don't roll a 7. So when you write 7 prime. So here again, 7 stands for the set of rolling a 7, not the number 7 itself, which I know sounds a little confusing. So we know the probability of rolling a 7. We kind of did this earlier. It was 6 over 36, which reduces to 1 over 6. All right. And let's see. How many ways can we not roll a 7? Well, remember the probability of E prime is just 1 minus the probability of E. So this is really just 1 minus 1 over 6. In fact, this is something I could have written up here. I could replace P of E prime with just 1 minus P of E in both of these, actually. So what we get is, there are a few ways of doing this. The best way maybe is just to clear denominators, so multiply top and bottom by 6. This is something we actually haven't seen in this class in particular, but it's something you can always do. You can always multiply top and bottom of any fraction by any number. Also, if you wrote it as 1/6 over 5/6, which is 1 minus 1/6, you'll get 1/6 times the reciprocal of 5/6, which is 6 over 5. The 6's cancel and you get 1 over 5. And that's exactly what's going to happen here. So notice these cancel, so we just get 1 on top. And after this 6 distributes, we get 6 minus 1, because that 6 cancels. And 6 minus 1 is 5. So we still get 1 over 5. So the way we write the odds here is either 1 to 5, so you can say it like this, or you can write the fraction, or you can write this colon notation, which is very often used, 1 to 5. So the odds for rolling a 7 are 1 to 5, meaning that there are 5 times many more ways to not roll a 7 than there are to roll a 7. So that's something to think about, but in any event, that's the best way to phrase it. Now, to follow up this question, part 2 asks, if we bet $1 on rolling a sum of 7, what should the house pay plus returning our $1 back, of course, if we roll a sum of 7 in order for the game to be fair? So all it means by the game being fair is just that they're using correct odds. So if you go to a casino that holds this game, rolling a 7 or something like that, then the betting odds should be 1 to 5. And if not, then it's not a fair game, which means either it's in your favor or it's not in your favor. But in any event, there that is. So we know the odds are 1 to 5 if the game is fair. So that means for every $1 we bet, well, if we actually roll a 7, then we get 5 times that many dollars back because there are 5 times as many ways we couldn't roll a 7. So the answer here is really just $5. So this literally is the ratio of ways you can win versus the ways you can lose. So really, this is why odds are so important when it comes to betting, because it kind of makes things a little easier to calculate, I guess, on the fly. So you can always just look at these odds for any particular game and figure out how much you'll get back, provided you win, of course, based on how much you'll bet. Anyways, that was basically it for chapter 8.2, so I'll see you in the next video for 8.3. Thanks for watching.